Hello and welcome to the LS Telecom web seminars. This is the third and last seminar of the series Smart Spectrum Solutions for Telecommunications Regulatory Authorities. I'm glad you tuned in. My name is Larissa Behrendt and I'm your host. I hope everyone had his or her morning, afternoon or even evening coffee if such a thing exists and feels ready to take part into this web seminar. Because this is what we want. We want you to feel comfortable with asking questions at any time. We want you to enjoy the seminar, and most important, we want you to take interesting insights and instructive facts with you from this format. So today's seminar is called Automated Radio Monitoring with LS Observer. It illustrates how regulatory authorities can detect, locate, and prevent interference and ensure safe and optimal frequency usage in the long term. The seminar further shows how our big data and AI solution SpectrumMap enables real-world-based spectrum management. Before my colleague Philip Abel is going to take over the lead, let me briefly introduce LS Telecom to those who may not know us yet. LS Telecom was founded in 1992 in Germany, and ever since, the company has substantially grown. Today, we are counting around 250 employees in over 10 countries, which is pretty cool, I think. And LS Telecom nowadays represents a globally leading supplier of system solutions and consulting services with the aim of unleashing the full potential of the radio spectrum. As such, we deliver fully integrated spectrum management systems, radio network planning, tools for different radio technologies, and of course, automated radio monitoring systems. In addition to the system solutions, we also offer consulting and engineering services. Our consultants are experts in the fields of regulatory policy and strategy, business planning and development, network planning and optimization, monitoring, and much more. Until today, we have provided our products and services to customers in more than 100 countries, and both our system solutions and our consulting services are based on a global know-how and experience that we have gained in more than 29 years. Come back to today's web seminar now. The seminar is scheduled for around 45 minutes, and after I stop talking, Philip's presentation will last about 30 minutes, such that we have another 10 minutes for question and answers. So you are more than welcome to ask or post questions during the web seminar into the chat window. And we will answer as many as possible of them during the Q&A session at the end. The web seminar will be recorded and made available for you. Within the next days, you will receive an email with a link to the recorded web seminar. Now, let me conclude with the introduction. Thank you once more for joining, and I will hand over to my colleague, Philip.
So, thank you, Larissa, and welcome from my side. My name is Philip. I'm the responsible product manager at LS for our spectrum monitoring solutions and the LS Observer system. So, today's presentation is about exactly this topic, about automated radio monitoring with our LS Observer solution. So first, what is LS Observer? With LS Observer, LS has a sensor-based automated spectrum monitoring system. What does that mean? So first, if you look at spectrum monitoring, we have this, as you can see here, a screenshot of our CMS software, the classical spectrum monitoring, a power versus frequency chart with a linked waterfall chart. But LS Observer is more than this, only traditional monitoring. We have sophisticated features like AVD, automatic violation detection, where the software automatically compares the live measured spectrum with the user-defined reference spectrum. And in case of any anomalies, will automatically trigger an alert. This could be, for example, interference or illegal frequency usage, for example, jamming. Then, if you have such an alert, you want to know where does the emission come from. And here LS Observer offers 3 different technologies to locate an emission source. We offer direction finding based on AOA. We have time difference of arrival and our own unique technology, gain ratio of arrival. LS Observer is sensor-based. Here you can see our hardware portfolio. So we have different monitoring units for different applications. So on the left side, you can see the fixed monitoring unit. Then we have further mobile and portable unit. And we even have a flying observer, a fully drone-based integrated monitoring system. So if I say system, all the LS Observer can be connected in one network. You can see a typical regulator network. So you have multiple fixed stations, you have portable equipment and, for example, mobile equipment. And all this equipment can be connected together and can be remotely or locally controlled. LS Observer is highly automated, so with LS Observer we are able to automatically record the entire spectrum of interest, for example 9 kilohertz up to 18 gigahertz permanently 24/7. And then the AVD automatically runs on the unit. That means any anomalies can be automatically detected. So when nobody is in the office or you don't have staff to do permanent monitoring, our system can automatically alert you, for example, via email. Based on this, alarms are generated and then the emission source can be located. So what does LS Observer consist of? We have on one side the hardware, our remote monitoring unit, so fixed, mobile, portable and flying, and we have our own unique DF system. And everything is controlled by one unified software, the LS Observer CMS Central Monitoring Software. And this combination allows a wide, it's called LS Observer. In the last web seminar, you heard about our spectrum management solution, MySpectra, and as monitoring, also like the ITU defines it, is an inherent part of spectrum management. We combine both worlds. We combine our spectrum management, MySpectra, and our LS Observer system. If you don't use monitoring in spectrum management, you will be blind. So spectrum monitoring is a really important part of spectrum management. What does this interconnection mean? So on the one side, the spectrum monitoring system knows then from the spectrum management about the license plan. It can do monitoring orders, so you can do from the spectrum management, you can do campaigns which the monitoring system will run, and then the monitoring system, the LS Observer, will deliver sophisticated data back to the management system, for example, occupancy data, so to see the channel utilization over time, and then the spectrum manager can base his assignment decisions, for example, on this real-world monitoring data, not only on theoretical data. Then coming to our hardware, here you can see the major internal parts of our monitoring units, whether if it's a fixed station or mobile unit. You can see we have a receiver inside, so a high-end radio receiver, internal processing power, a modem for the network communication, and what is important, a large internal storage. That reflects the philosophy of LS Observer to permanently record everything, the entire spectrum of interest, to never miss any event. And then the LS Observer has powerful features to analyze not only live data, but especially stored data. You can make use of stored data. You can go back in time. For example, if you come at your office in the morning, you can check what happened during the night. You can detect, analyze, quantify, and locate interference based on stored data. So you can even do the allocation based on this stored data. You can use stored data to set a reference baseline for future measurements. So you can compare the future measurements, and if there are any anomalies, our system will automatically identify it. You can create meaningful long-term spectrum usage statistics and reports to support the spectrum management decision-making. And which will also be the topic of today, you can create spectrum usage and coverage maps with our innovative tool SpectrumMap. Here you can see now some pictures of our fixed monitoring unit. This can be really flexible in store for permanent outdoor monitoring. So you can simply put it on a mast like you can see here on the right side on top of a building or just on a lantern pole. On the left side you can see our demo system which we have here at the local airport. Then our transportable monitoring unit, it includes a large battery. It can be used for temporary fixed measurement where you can place it, for example, 1 week on top of a building, and it can be used inside a vehicle for drive tests. Then we have further units. We have portable units. Here you can see our portable monitoring unit for signal hunting, signal homing, where you have the emitter localization on the last meters. This is supported with a special view in our software. And here you can see our unique direction finding solution, the AOA1XX system. What is unique about this system is that you can not only do direction finding live as usual, but also based on stored data with the so-called DF time travel technology. Coming to our LS Observer CMS software, it's a really powerful software which supports a wide range of features. Here you can see some highlight features, for example, ITU compliant measurements, you can do a scan, you can do job scheduling, you can do the recording. Based on those recording, you can do analysis, you can place the analysis in reports, you can do occupancy measurement, and on the other side you can do localization via DF, TDOA or GOA+. Now some highlights and some overview of the software which I have captured in a short screen video. Here you can see the LS Observer CMS software, the monitoring system overview, where you have all connected monitoring units and you can see them on the map. You can simply add new monitoring units to your network. And then with measurement control, you can select any unit and start a measurement. Like for example here, a frequency range scan. You can set up the transmitter at the receiver parameters, and then you can see the live spectrum the view bigger. It's a really interactive mode. You can just zoom in. There are different operations. For example, you can move the measurement vertically. So you can see a really interactive chart. You can always go back into your actions and also possible to apply multiple curves, like for example maximum hold curve for fluctuating signals. You can also apply markers inside here. Just double click on the signal and then you have the marker information down here, and you can apply the marker to the next peak, apply a second marker. We also have the delta marker option. So this is a basic spectrum monitoring live operation. Now to the AVD, to the automatic violation detection, where the user can define a reference spectrum. So he can build a mask per channel, a mask defining the reference level, so the normal level you expect, the upper tolerance and the lower tolerance, so where the signal can fluctuate in. So if the signal exceeds those tolerances, an alert will be triggered. How does it look like? So you first need to start a measurement, then give the AVD log, so all alarms are logged, a name, and then start the AVD task which you've created in before. And now the analysis is permanently running on the monitoring unit itself. You don't need a connection. It will execute it by the monitoring unit, by the remote unit. And here you can see the alerts for the ATC. So I have a lot of ATC channels here, 25 kilohertz in bandwidth. You can see I've set up that as soon as the signal pops out from the noise, it will trigger an alert. This now only for illustration purposes. And now we can see the AVD log, which is in the stored data, where you can see the alarm history over time. So you can see in which channel was an alarm, how long did it last, and when did it get to normal. So you can see the different coloring. Green, everything is good. Red, you have alarms. Now in this example, for sure, a lot of alarms to illustrate you. In reality, hopefully not. Yeah, this AVD, you can do it either you can say, okay, I want to see any signal as soon as it pops up from the noise. So I say, okay, my reference level is noise, or I define a normal level in this frequency range. For example, this channel is normally used with a certain level, and I can say, okay, the signal can fluctuate inside certain ranges, and once these thresholds are exceeded, you get an alert. How to create the things? Yeah, you can do for sure everything manually, but that's a lot of work. So with CMS, you have further option. Option 2 is to do really to monitor your license condition. You can import from Spectrum Management or from Excel file, you can import the license transmitter information. So you can in your license database, you have, for example, for a transmitter, you have the location and the maximum allowed radiated power. And exactly from this maximum power, our software automatically calculates model calculates the expected receive level at the single monitoring unit if the emitter would emit according to his license conditions. So you have a reference, so you can monitor the license conditions. If the emitter violates the license conditions, so for example with too high power, you can see it with this AVD wave propagation calculation technology. You can for sure then add again a tolerance where the signal can fluctuate in, and you can also adapt everything manually if this the calculation is for you a bit too optimistic. For example, you can always manually interact, and then you can just simply, as it is, you can monitor your license conditions. Option 3 would then to do the whole thing based on stored data. So you can do a reference spectrum at a certain location and take this as a baseline for future AVD. So it takes the average level during this measurement and the fluctuation and builds up a mask. And then if you come back again the next week, for example, like you can see here, if in this example, it's the L1 GPS, if the noise level certainly raises in comparison to the measurement reference situation, you will immediately get an alert from the system. And this alert you can see as an optical highlight, or it can be automated that you will automatically get an email from the system. So if you don't need someone who permanently looks at the screen. And now our newest innovation coming in spring next year will be using artificial intelligence for AVD. We call it smart AVD, and this will bring AVD even to the next level. With this, the AI is able to learn a spectrum on site, to learn its characteristics, and to say, okay, that's the normal thing. If there is any anomaly, the AI can automatically identify it and classify it. Okay, now back to the stored data. So I introduced it already. You can do a lot of features based on stored data with CMS. You have a list of all stored data in the monitoring overview. Just select one data and then you can filter the data. You don't need to display the whole recording. You can limit it to a certain frequency range and a certain time range. For example, to analyze a reported interference. And then you can slide through the time, and you can also zoom into certain events to analyze it in detail. Then for the recording data, LS Observer also provides frequency channel occupancy data. And occupancy data, with this you can see the channel utilization over time. You can see we have here color coding. Red means that during the ITU-defined time interval, for example, for 5 minutes, permanently a signal was in air. So the channel is occupied. Like you can see here for FM channels, 100% occupancy. Going to the colder colors, for example, if only half the time, 2.5 minutes, a signal was on air, you have only 50% occupancy. And here you can see right from the FM, you have the ATC bands, you have a lot of white, there is nothing, and then you have blue, where you can see that's the typical ATC traffic, so sometimes pilot speak, sometimes tower ground control speak, so not so much occupancy. And you can see here also a red line in between. It's on the more to the right, it's the AT signal of the airport, so a permanent emitter, permanent electronic voice. You have 100% occupancy. On the left side you have also a red line, which is interesting because during the night it suddenly stops. That you can also see with occupancy data. So it's the instrument landing system. And you can see also on the right side the difference between day and night. You can see if you go from the lower end up, you can see in the night hours the traffic reduces. You can see more white, and then in the morning hour there's more traffic again. All this you can see from occupancy data. It's a really valuable tool for also for spectrum management to decide which channels have overloads, which channels are still free to use. Then coming to localization, how you can locate a signal in CMS or with the LS Observer system. The first thing is direction finding with our DF system, our AOA1XX system. Here you can do DF based on stored data, and for this measurement we did a measurement from 80 megahertz up to 1 gigahertz. You can select any signal inside this range and can do direction finding on it. That's a unique DF time driver technology, so you can do this not only live but on stored data. So you have a line of bearing on the map, and you can also let the software calculate a heat map. This is especially of interest if you have multiple line of bearings. Then another technology with omnidirectional antenna is our GRA plus technology. Gain ratio of arrival is a term also used by the ITU, where only omni antennas are used and the level is compared, the received level from multiple locations. Now, this technology normally assumes that there is free space, and if you have, this works in free space for sure, but in urban environments, you have not really good accuracy. It won't be accurate at all. So what we do here, that's why we have added this plus to GRA. We do wave propagation calculation. So we consider any obstacles between the searched emitter and our receiver. And by considering this, we make this GRA to a really precise method. You can see here we located the ATIS transmitter of the airport, and it's also illustrated at the heat map. So you can do this on stored data. Now we can see time difference of arrival. It's a well-known method where you use the time differences of arriving wave at least 3 measurement points, so 3 monitoring units. And here you simply select it from live measurements. And then you can see, like in the other technologies, a heat map. In this case, a live heat map. And we did some aggregation here where the heat map gets better and better. You can see the circle of red gets smaller and smaller. Even if this situation is not perfect for TDOA because the signal source is outside the polygon, the sensors are opening, you can see you can, with a certain accuracy, I think here of 50 meters, you can locate the signal. Would it be inside the polygon, you would have a really precise accuracy. But due to this geometrical limitation of TDOA and bandwidth limitation, we have also other methods available in CMS, so the user can decide which is the best method for his special use case. Now let me come to the SpectrumMap, to our big data visualization platform for modern spectrum monitoring. Yeah, what is SpectrumMap? SpectrumMap uses big data collected from monitoring. So it can use data from fixed station, it can use data from drive tests and any other monitoring units from LS Observer or even third party. And if you do a drive test, you may know this view you can see here on the right side with some dots on the line where on the street where you did the drive test, so you can see the level differences. If you do it like on the right side for this project in Shanghai, if you drive around with a lot of vehicles for a few days, or it was even a week, you have such a big picture like you can see here on the right side. But that's a view, you don't have a continuous picture, you don't have a really meaningful picture. And with SpectrumMap, we want to combine all this data together to give the user a continuous picture of his spectrum in an urban area, for example. So he gets a map, so all the data is mined and fused to uh, to visualize multiple different maps, also dynamic maps, comparison maps, and this is SpectrumMap. You don't have single dots, you have a continuous map of your spectrum, and this is really valuable, especially also for spectrum management, where you want to see what is happening in reality. How does it look like? So SpectrumMap has a web-based UI. You simply open it in your browser. And then you have a map of the current location. So you just, if you want to have a spectrum map, you just select a vector here, an area where you want to do the calculation. And then you have multiple calculation options. Then you select your band of interest, for example here, GSMR, so railway. And then you get a map of the field strengths. And you can see here it's color coded. You can also adapt the coding. So red means there's higher field strength. And you can see it's especially around the railway as we are here as in GSMR. So you have a continuous picture of your spectrum. You can also do it as a coverage analysis. So you can say, okay, at a certain level, I assume it is covered. As a level below, it's not covered. So you have this covered, uncovered view. And this is really interactive. You have also dynamic views where you can just simply slide through a frequency band channel by channel. So you can compare how the spectrum changes channel by channel. And this is also available as a time slider. So really interesting. You can see how the spectrum changes, for example, per weekday. If you have long-term analysis, you have a really big information basis here with SpectrumMap. So another project we did, we were really pleased to do this a trial in the modern city of Dubai. Here can see an analysis result of 1 day of drive test. What we did here, just show you the next slide, we just equipped a standard vehicle. We put a antenna on top of it, LS observer antenna with a magnetic base and an LS observer unit inside the vehicle, a portable unit, and let the measurement permanently run. This was really automated, so you don't need a driver who is a monitoring expert. You can program it in such a way as soon as the vehicle reaches a certain area, the recording will automatically begin with the predefined parameters. Once the vehicle is outside the area, it will stop the recording. And then we recorded over 268 gigabytes of data. We drove around 630 hours through the entire city. And then back on the parking garage, everything was automatically backed up. So from the LS Observer device to the SpectrumMap server, and everything was automatically processed. And then, for example, the Spectrum Manager can just come the next day in his office, simply open the browser, open SpectrumMap, and look at the analysis picture of the last day. And then you can have such a nice picture like you can see here with a different distribution of field strengths. It's a field strength map. And in this case, we did 3 days of drive tests. You are also able then to combine all 3 days together. Now you can do this for sure with multiple cars for this, especially for this job. But what we see here is the future is to use public transport. to use, for example, buses, taxis, the tram, garbage truck, or other things, yeah, other public transport. Those kind of vehicles drive around the entire city, the important part of the city, the whole day. So you just need to equip it with monitoring equipment and you get a really high data density. It can collect a lot of data, which gives you a very meaningful picture. So it's really, I would say, more ecological and also environmental friendly. You don't need your own car fleet. You don't need stuff. You can just simply use the public transport for this. And yeah, we see this as really the future for urban monitoring, especially if you have really the cells are getting smaller and smaller. If you look at 5G, you can capture really on the ground, on the street level, what's happening in the spectrum, and this permanently day by day in a really dense way. Coming to the density, just a bit to describe the spectrum map, to describe the accuracy of a map. If you imagine in this area here, if you want to have a precise map, how does it work? So if you look only at the purple line, which follows the highway, you get not really just drive this way. If you drive the purple line plus the red line, you circle around the area, you get a more precise spectrum map. If you even want it more precise, you can use then it in addition also the blue line, so you have a really dense picture, a really detailed spectrum map. If you think about, again, public transport, it looks like, for example, bus lines. So the bus lines are typically really dense inside of the city area. So you can use, again, an argument to use public transport, because if you need to drive all this, it will take time and you need stuff for this. What are the use cases then for SpectrumMap? I've listed some exemplary use cases. For example, to evaluate the cellular coverage of 3G, 4G or 5G, you can see the aggregated view for the total band. So you can see the total availability of cellular services, for example, 5G. And you can look at the single providers. You can look at which provider does provide coverage in which areas, which provider has the best coverage. This you can see, for example. And you can also do it in the other way. You can look at the uplink. You can look at the usage. Where are 5G? Where's 5G, for example, the most used? Yeah, where you have areas of really dense usage or low usage. Or you can see from SpectrumMap. Then, for example, if you look at IoT, Internet of Things, where it is available, look at the downlink. Is it available in smart city areas or industrial areas? Look at the uplink where it is really used. Look at Tetra, for example, how many channels are used and where are there overloads. You can dynamically step through the Tetra channels, or the same for Wi-Fi. These are only examples. You can do this for any service you want. And what is especially of interest, that you also can compare multiple days, yeah, or even months or years if you do it on a permanent basis. So you can see, does the spectrum change during different days, during different months. You can see if there's, for example, capacity left on a certain channel weekday. Then you can think about modern technologies like spectrum sharing concepts, where you can say, okay, my channel Monday and Friday, it is not heavily used, so and a party, or you can do a location-based assignment. So with the spectrum map, you see the location where it is used, where it is not used, where you have free capacity. So especially for urban environments, you have a really crowded spectrum. You can have the basis for spectrum sharing concepts with this spectrum map solution. What you can also do is to evaluate radiation hazards, to show to illustrate a map of radiation over the city, and then you can prove to public, for example, that there are no radiation hazards, that all radiation is within the limits. That's also an application of SpectrumMap, and many more. These were only now exemplary use cases of this. Okay, then this was my presentation of our LS Observer system and our SpectrumMap solution. Now let me come back to my colleague Larissa for this question and answer part.
Thank you, Philip, for the very interesting presentation. Now it is time for Q&A. So if you have any question, please feel free to ask it in the chat window right now. Okay, let's start, Philip. Is LS Observer data good enough to allow dynamic spectrum sharing for DSS or shared bands like CBRS?
That depends what you mean with good enough. With LS Observer, you have a high-end receiver which can be used in different accuracy levels. Yeah, you can have a really narrow step width. Do not understand your question completely what you mean with really good enough. Maybe you also mean SpectrumMap, if this detailed enough. I think that is the question. Like I showed you before, the detail grade depends on how dense your data is. Yeah? If you only drive around the city, just one street and a second street, it's SpectrumMap calculates it interpolates the data in an intelligent way, but between those two roads, if you look at a specific point, just maybe 10 meters, yeah, you don't have the accuracy. Yeah, you need to drive more streets which are beside the first and the second street. So it depends really on the density of data, how precise the results are.
Okay, thank you. There's an addition, good enough as in so reliable that indeed one can allow shared usage with maintaining of QoS.
Quality of service, okay.
Yeah.
Yeah, definitely. We have already experience with such spectrum sharing approach. We have also studies here at LS, so if I can answer your question, definitely good enough to do this use case. That's why I also mentioned this use case. That is the best data source you can use for such spectrum sharing methods.
Okay, thank you. So there is a comment from Kevin. He says, it's interesting to view how this works. It allows in order to check where spectra EMC shows that all channels within an area are congested, but on the ground, there is a little radio use. Does this scenario allow greater sharing of channels, particularly for services such as business radio, PMR, where you can in theory increase the sharing on voice-only channels, but unlike for data channels where you have consistent polling? So this is a really
so really detailed question. Yeah, interesting. Definitely for Spectra EMC, for example, where it says in theory that all channels are full, are congested, with spectrum monitoring, you can see in parallel the reality. And those systems will be interconnected. It's already on the roadmap, especially this scenario that you can have from SpectrumMap or CMS, detailed and sophisticated view about this channel, if it can be used for spectrum sharing, and if it can be used, if it's in theory, if it's full, but in reality, it's the other way. So that's the really great thing, that you can combine the theory with the reality. That makes really spectrum management on a better level, on a real level. And you need this. You need the reality for spectrum sharing. Only from licensed data, it won't work.
Okay, thank you, Philip. Are there any questions left? Because now it's a time to ask them. but I think there are no questions. So yeah, Philip, thank you very much for your presentation.
Thank you.
And now to an end of this web seminar, let me say a few words. As I already mentioned before, this seminar has been the last of our web seminar series this year. We're having a short winter break and we will back with a new web seminar series at the beginning of next year. If you want to stay tuned about this, feel free to subscribe to our newsletter or follow us on social media, where we always keep you up to date. And also, you will get to know who's behind different teams of LS Telecom, and you don't miss when we look behind the scenes of certain areas of our company. So besides web seminar, we also offer online training courses, and you will find our current training offerings on our website or on our newly established LS Telecom web store. And you can also register for the training courses via the web store. And I could imagine that our spectrum monitoring trainings at the beginning of December might be interesting for you. So feel free to have a look, and we would be very happy to welcome you to our trainings. If you have further questions concerning our products or services, please do not hesitate to contact us at any time. And now let me thank you again, everyone, for tuning in. We would be glad if you keep in touch with us. I hope to see you again during our next upcoming web seminars or during our trainings. Until then, I wish you all the best, and most important, stay safe.